Are you ready to learn more science facts? Today I have prepared for you 10 interesting science facts with explanations. I hope this video will be useful for you. Well, let's get started. Did you know that the most abundant element in the Earth's crust is oxygen, followed by silicon and aluminum? The Earth's crust is composed of a variety of elements, with oxygen being the most abundant element in this outermost layer of the Earth. Oxygen makes up about 46.6% of the Earth's crust by weight. Following oxygen, silicon is the second most abundant element in the Earth's crust, constituting approximately 27.7% of its composition. Aluminum comes next and is the third most abundant element in the Earth's crust, making up around 8.1% of the crust's weight. These elements, oxygen, silicon, and aluminum, play critical roles in the composition and structure of the Earth's crust. Silicon is a major component of silicate minerals, such as quartz and feldspar, which are abundant in the Earth's crust. Aluminum is also found in various minerals and rocks, contributing to the overall composition of the Earth's outer layer. Oxygen, silicon, and aluminum are fundamental elements that shape the physical and chemical characteristics of the Earth's crust and influence many aspects of our planet's geology and environment. The statement that the most abundant element in the Earth's crust is oxygen, followed by silicon and aluminum, highlights the fundamental composition of the Earth's solid outer layer. We will now take a closer look at each of these elements and their importance. First, oxygen is the most abundant element in the Earth's crust, accounting for approximately 46.6% of the crust's total weight. It is a crucial component of many minerals, oxides, and silicates found in the Earth's crust. Oxygen is not only abundant in the solid crust, but also plays a vital role in the Earth's atmosphere and hydrosphere, contributing significantly to the planet's overall composition. Second, silicon is the second most abundant element in the Earth's crust, comprising around 27.7% of the crust's composition. Silicon is a major constituent of silicate minerals, which are the most abundant group of minerals on Earth. Silicates form the building blocks of rocks such as granite, basalt, and sandstone. Silicon also plays a crucial role in the formation of minerals like quartz, feldspar, and mica. Aluminum is the third most abundant element in the Earth's crust, making up approximately 8.1% of its weight. While not as prevalent as oxygen and silicon, aluminum is a significant component of various minerals and rocks. Aluminum is commonly found in minerals like feldspar, bauxite, and clay minerals. It is widely used in various industries due to its lightweight, malleable, and corrosion-resistant properties. The abundance of oxygen, silicon, and aluminum in the Earth's crust reflects the geologic processes that have shaped the planet's surface over millions of years. These elements, along with a variety of others, form the diverse array of minerals, rocks, and geological structures that make up the Earth's crust. Understanding the distribution and composition of these abundant elements is crucial for geologists, as it provides insights into the Earth's history, formation, and ongoing geological processes. The center of the Earth is estimated to be at a temperature of about 6,000 degrees Celsius, 10,800 degrees Fahrenheit. The estimate of the Earth's core temperature being around 6,000 degrees Celsius, 10,800 degrees Fahrenheit, is based on scientific models and indirect measurements. So, why the Earth's core is believed to have such high temperatures? Firstly, heat from formation. When the Earth initially formed around 4.5 billion years ago, the collision of materials and gravitational compression generated a significant amount of heat. This heat has been retained within the Earth, contributing to the high temperatures at the core. Secondly, radioactive decay. Radioactive elements like uranium, thorium, and potassium are present in the Earth's interior. The decay of these radioactive isotopes releases heat energy, adding to the internal heat of the planet. Thirdly, gravitational compression. The immense pressure at the Earth's core due to the weight of the overlying layers causes compression and heating of the materials in the core. The next reason, geothermal energy. The heat generated within the Earth's mantle and crust is also transferred towards the core, contributing to its elevated temperature. And finally, geophysical observations. Indirect measurements, such as seismic wave velocities and magnetic field observations, provide insights into the properties and composition of the Earth's core. These data, along with computational models, help scientists infer the core's temperature. The core of the Earth is divided into the outer core and the inner core. The outer core is believed to be primarily composed of molten iron and nickel, while the inner core is a solid sphere primarily made of iron and some nickel. The temperatures in these regions vary, with the inner core being hotter than the outer core. By studying the Earth's internal structure, geophysical phenomena, and rock samples, scientists have developed models to estimate the core's temperature. The high temperatures at the Earth's core play a crucial role in driving geological processes, generating the planet's magnetic field, and influencing volcanic activity and plate tectonics on the Earth's surface. Jupiter's moon Europa is believed to have a subsurface ocean that could potentially harbor life. Europe. No, not the one you're thinking of. Europa, one of Jupiter's many moons, is a fascinating world that scientists believe might hold life. Here's why. Hidden ocean. Beneath Europa's icy crust, there's strong evidence for a massive ocean of liquid water. This ocean is likely even bigger than all of Earth's oceans combined. Evidence for Europa's ocean comes from several sources. Studies of Europa's magnetic field suggest a salty liquid layer beneath the icy surface. The flexing of the moon due to Jupiter's gravity also hints at a deep, mobile ocean. Scientists estimate this subsurface ocean could be massive, possibly containing twice the amount of water found in all of Earth's oceans. Salty and favorable, the water in Europa's ocean is thought to be salty, similar to Earth's oceans. This saltiness is important for life as we know it. Salty water is crucial for life as we know it. The presence of salt in Europa's ocean is encouraging because it allows for important biological processes. Potential energy source. Jupiter's powerful gravity constantly pulls and stretches Europa, creating a churning internal environment. This churning could be a source of energy for life forms, similar to how deep-sea vents on Earth support unique ecosystems. All these factors make Europa a prime candidate in the ongoing search for extraterrestrial life. Scientists are very interested in exploring Europa's ocean to see if it truly holds the ingredients and environment to support life. There are even missions being planned to explore this possibility. Despite the challenges, Europa's potential for harboring life makes it a target for future space exploration missions. Scientists are actively developing technologies to explore Europa's ocean and unravel its secrets. In conclusion, Europa's subsurface ocean, with its potential for liquid water, energy sources, and the right chemical ingredients, makes it a fascinating target in the ongoing search for life beyond Earth. Future exploration missions might be able to shed light on whether this icy moon holds the key to unlocking this exciting possibility. The first photographs of the far side of the moon were taken in 1959 by the Soviet spacecraft Luna. For centuries, humanity only saw one side of the moon. This is because the moon is tidally locked with Earth, meaning the same side always faces us. In 1959, that all changed thanks to the Soviet Luna 3 spacecraft. Scientists had theories about what the far side might look like, but there was no way to confirm them until the development of spacecraft technology. The year is 1959. The space race is heating up, and the Soviet Union is pushing the boundaries of space exploration. One of their triumphs in this era was the Luna 3 mission, which gifted us with the first-ever photographs of the moon's far side. Launched in October 1959, Luna 3 was specifically designed to capture images of the lunar far side. It wasn't a landing mission. Instead, it flew past the moon and took pictures as it looked back at the sunlit side that's invisible from Earth. The quality of the images captured by Luna 3 wasn't high resolution by today's standards. They were blurry and lacked detail. However, their historical significance is undeniable. These were the first ever photographs of a celestial body that humanity had never directly observed before. The Luna 3 mission remains a pivotal moment in space exploration history. It marked the first time humanity could see the entirety of the moon, not just the familiar face. Want to know even more science facts? Subscribe to the channel because it has daily interesting and shocking scientific facts. The Earth's atmosphere is composed of approximately 78% nitrogen, 21% oxygen, and trace amounts of other gases. Our planet Earth is surrounded by a layer of gases called the atmosphere. This atmosphere acts like a giant blanket, protecting us from harmful radiation from the sun and helping regulate Earth's temperature. The atmosphere is made up of mostly two main gases. Nitrogen, 78%. This abundant gas plays a crucial role in life on Earth. It dilutes the oxygen we breathe, preventing rapid burning, and is also used by some living things like plants to create proteins. Oxygen, 21%. This vital gas is essential for most forms of life on Earth. Living organisms use oxygen in cellular respiration to generate energy. While nitrogen and oxygen are the dominant players, there are other gases present in much smaller quantities. Argon, 0.9%. This inert gas doesn't react much with other elements and plays a role in atmospheric stability. Trace gases, 0.1%. This category includes water vapor, carbon dioxide, methane, and others. These gases play important roles in weather, climate, and some are even greenhouse gases that help trap heat near Earth's surface. The specific percentages of these gases are crucial for life on Earth. Too much oxygen could lead to widespread fires, and less oxygen wouldn't support complex life forms. The presence of trace gases like carbon dioxide also plays a vital role. While an excess of carbon dioxide can contribute to global warming, some amount is necessary for plant growth, which is the base of the food chain. It's important to note that the atmosphere isn't perfectly mixed. The concentration of some gases, like water vapor, can vary depending on altitude and weather conditions. In conclusion, Earth's atmosphere is a complex mixture of gases, each playing a vital role in supporting life and regulating our planet's climate. The universe is estimated to be about 13.8 billion years old, according to the latest measurements of cosmic microwave background radiation. The vast universe we inhabit is incredibly old, and scientists can estimate its age by studying a special kind of leftover radiation, the cosmic microwave background radiation. The prevailing cosmological theory is the Big Bang, which suggests the universe began from a very hot, dense state and has been expanding and cooling ever since. The CMB radiation is a faint echo of this momentous event. It's everywhere in the universe, filling all space. Imagine the universe as a giant balloon inflating. As the balloon expands, the heat from its initial hot state gets stretched out and thins out, becoming cooler. The CMB radiation is like the faint afterglow of that heat, and by measuring its properties, scientists can estimate how much the universe has expanded and cooled since the Big Bang. Sophisticated space missions like the Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck satellite have precisely measured the CMB radiation. These measurements take into account factors like the temperature fluctuations and tiny ripples in the CMB, which provide clues about the universe's age and evolution. Based on the detailed analysis of CMB data, scientists estimate the current age of the universe to be around 13.8 billion years old. This is a very precise number, and ongoing missions might further refine this estimate. In essence, the cosmic microwave background radiation acts as a cosmic tape recorder, preserving a faint signal from the distant past. By deciphering this signal, scientists can estimate the universe's age and gain a deeper understanding of our cosmic origins. DNA, the blueprint of life, was discovered by James Watson and Francis Crick in 1953. DNA itself was actually discovered much earlier, in the 1860s by a Swiss chemist named Friedrich Miescher. He found an unknown substance in white blood cells that he called nuclein. Later, this substance was identified as deoxyribonucleic acid, or DNA. What James Watson and Francis Crick did in 1953 was a groundbreaking discovery, but not the discovery of DNA itself. They unraveled the structure of DNA, revealing its now famous double helix shape. This structure was the key to understanding how DNA stores and transmits genetic information, earning it the title Blueprint of Life. Miescher's discovery of DNA and the research of Rosalind Franklin on X-ray crystallography of DNA were crucial stepping stones that laid the groundwork for Watson and Crick's breakthrough. In conclusion, DNA existed long before Watson and Crick, but their discovery of its structure revolutionized our understanding of life. It's a testament to the collaborative nature of science, where new findings rely on the foundation built by previous researchers. Let's move on to some human body fact. The human brain is the most energy-consuming organ in the body, using about 20% of the body's total energy. Unlike muscles, which can store energy and rest, the brain is constantly active, even during sleep. It's responsible for complex functions like thought, movement, sensation, and perception. This constant activity requires a steady supply of energy to keep things running smoothly. The brain's primary fuel source is glucose, a type of sugar. Brain cells, called neurons, use glucose to generate ATP, adenosine triphosphate, the energy currency of cells. These neurons are constantly firing electrical signals to communicate with each other, and this electrical activity requires a substantial amount of energy. The brain also has a limited capacity to store energy reserves. Unlike muscles that can store excess glucose as glycogen, the brain relies on a constant supply of glucose from the bloodstream. This means a consistent flow of energy is crucial to maintain proper brain function. While 20% might seem excessive for an organ that makes up only 2% of our body weight, it's essential for the brain's complex functions. The intricate network of neurons and the constant communication happening within the brain necessitate this high energy expenditure. Ensuring the brain has sufficient energy is vital for maintaining cognitive function, memory, and overall well-being. A lack of proper fuel can lead to fatigue, difficulty concentrating, and even impaired brain development. In conclusion, the human brain's remarkable complexity and constant activity come at an energetic cost. This high energy consumption reflects the brain's critical role in coordinating all bodily functions and shaping our experiences of the world. The Milky Way galaxy is estimated to contain more than 100 billion planets. Stars are typically born in giant clouds of gas and dust called nebulae. During the star formation process, leftover material from the nebula can clump together and form planets. So, wherever you find stars, you're likely to find planets as well. The Milky Way is a spiral galaxy, estimated to contain between 200 billion and 400 billion stars. With so many stars, the odds are high that a significant portion of them have planets orbiting them. While we can't directly observe planets in most other galaxies, astronomers use a technique called the transit method to detect planets in our own galaxy. This method involves observing a star for dips in its brightness, which can indicate a planet passing in front of it, blocking some of the light. Based on the number of exoplanets, planets outside our solar system, discovered using the transit method, scientists estimate that most stars likely have planetary systems. Extrapolating from these findings suggests billions of planets could exist in the Milky Way. It's important to note that the exact number of planets in the Milky Way is still an estimate. Depending on the methodology and assumptions used, different studies suggest figures ranging from 100 billion to several times that amount. With the ongoing development of telescopes and space exploration technology, scientists are constantly refining their estimates and discovering new exoplanets. The quest to find Earth-like planets within the habitable zone of their stars is a major focus of ongoing research. In conclusion, the Milky Way galaxy is a treasure trove of stars, and with so many stars, the estimates suggest a mind-boggling number of planets could be out there. As our technology advances, we may one day have a more precise count and potentially even discover planets that could harbor life. The speed of light in a vacuum is approximately 299,792 kilometers per second. The speed of light in a vacuum, often denoted by the symbol c, is indeed an incredibly fast 299,792 kilometers per second, or roughly 186,282 miles per second. It's a fundamental constant of nature, meaning it has the same value everywhere in the universe and doesn't change depending on the motion of the light source or the observer. The speed of light is a crucial concept in physics because it forms the basis for many important theories, including Einstein's theory of relativity. This theory establishes that the speed of light is the cosmic speed limit, meaning nothing in the universe can travel faster than light. Electromagnetism. Light itself is a form of electromagnetic radiation, and the speed of light dictates how electromagnetic waves propagate through space. It's important to note that the speed of light in a vacuum is the ultimate speed limit. However, light can slow down when it travels through a medium like water or glass. This is because the light interacts with the particles in the medium, causing it to travel at a slower pace. Overall, the speed of light in a vacuum is a fascinating constant that underpins our understanding of the universe. It's a reminder of the vastness of space and the incredible speed at which light races through it. That's all for today. Thank you for watching. See you next time.